Yeah. So I'll begin this talk, and the topic I chose to talk about is categorical logic and Topos theory. So let's begin by saying that this is an informal introduction, right? I guess many of you don't have a background in logic, and I think it's more appropriate to give a more informal notion, introduction to the topic. So I will try to cover these three main issues: logic and set theory, topos theory, and categorical logic. So the first question is, what is logic, right? Well, I can try to answer that question by saying that logic is what rules thinking, right? Is the rules, general rules behind rational thinking, right? But that's just too general. So I'll give the answer by saying how to do logic and how people do logic nowadays. So that's another question. Another question. When are two sets equal? Well, the answer is when they have the same objects. But usually, someone might tell you that two sets are equal when for every x and for every y, they will answer that question giving a formula or a sentence in this language here. For every x and for every y, x equal y if and only if for every z, z belongs to x if and only if z belongs to y. That's a sentence that we say that is in first order language. So I'm giving this example of um, an axiom of such theory because this axiom is in this axiom you can see in red what is considered the logical symbols. So this is the extension axiom of set theory, and set theory is the basis, is the fundamental theory behind mathematics, right? So mathematics can be translated into um, well-known symbols, and the rules that govern behind those symbols are very well known, and they compose what we call today symbolic logic. So logic is basically this: you translate your sentences, your language, your formal language into symbols and into operations, kind of algebraic operations using those symbols. Besides, we have those symbols here that receive those names, right? Negation, conjunction, disjunction, implication, universal quantifier, existential quantifier, and also we will work with this symbol here for truth or tautology, and this symbol for contradiction, right? And negation and means the word not, conjunction means the word and, disjunction, or implication, expression if, then, universal quantifier is for all, and existential quantifier means there is, right? So those are the main logical operators we use in your day life as we are studying mathematics, right? So there's actually nothing new in that. With those logical symbols plus variables, we can build propositions, sentences, and formulas. I will not go deep in making any difference between those three ideas, right? But basically, if you have a sentence, you can ask yourself or ask somebody else, sentence P, is P true, right? And to answer that question, we must give a proof of P in case P is true, or a proof of not P in case P is false. But another question, what is a proof? Well, basically, a proof is a well-founded, finite list of sentences built using logical rules. What do I mean by that? Imagine I have a sentence sigma 1, sigma 2, and as a consequence of those two sentences, I have the sentence sigma 3. And if I take sigma 3 and sigma 4, as a consequence, I will have sigma 5. Um, and to get sigma 3 from sigma 1 and sigma 2, I will have a very specific rule that will look kind of an algebraic rule. And the same applies to go from sigma 3 and sigma 4 to sigma 5. Sigma 1, sigma 2, and sigma 4 are called our assumptions, and sigma 5 is our conclusion. It is well founded because we have to begin somewhere, and it is finite, at least in parentheses, because it must end, right? A proof must end, but there are some kinds of logic where that accepts infinite list of sentences, infinite proofs. So just some terminology that might be I might refer to somewhere. This is called a sequence, right? And also, this is also called a sequence. So a proof is just a list of sequence that are built using logical rules. And now I'm going to how it works. Well, logic deals with preservation of truth. So if we assume sigma 1, sigma 2, and sigma 4 are true, then sigma 5 is going to be true. And this kind of tree here with sequence is a proof, technically saying, right? Basically, any proof you use in mathematics, right, can be translated into a list of sequence. And here we have some inference rules. So I said that we go from one step here to another using logical rules. And those are also called inference rules. And they are quite very simple, right? And they try to, they correspond to strategies we use to prove propositions. So here's some a very common inference rule. Imagine that the Greek letters represent sentences. So we have a rule that say that from phi and psi, we may infer phi, right? So the from the truth of the sentence, of the conjunction of phi and psi, we infer or they imply psi. Here we have another inference rule. If um, phi implies psi and psi implies gamma, we have that phi implied gamma. Here another example. Is introducing the conjunction, and here another example, right? And I will not go on details, but this inference rule has a special name, which is modus ponens, and this inference rule here is just proof by contradiction. Remember that these symbols represent contradictions. So it is just saying that if we assume the negation of a sentence, and from that we derive a contradiction, then that sentence is itself true. So we have a lot of many other rules, but basically they look kind of the same, and it's a mechanical, almost a mechanical process by dealing with that. I'll give a definition of the logical definition of a theory. A theory for a logician is a set of sentences closed under the inference rules, right? We say that a subset of a theory T is a set of axioms if every sentence in T can be proved from the sentence in gamma, right? Upper gamma. Yes, yes. Yeah. So if you can take any set of sentences and call that set your set of axioms, and uh, then mechanically, right? A computer can do that. Apply the inference rules, and every sentence which can be proved using the inference rules, will belong to the theory of that set of axioms. So, with this little background in logic, I can try to explain a little bit what is ZFC, right? Zermelo-Fraenkel with choice. Those are the axioms for set theory. And beyond logical symbols, right, and the logical concepts, the only thing in ZFC that is not considered a logical concept is the concept of set. In ZFC, we do not define what is a set. We just say that there are some things that are sets, and that those things satisfy some axioms, the ZFC axioms. So in ZFC, there is the answer to the question, what is a set? Is something that satisfies the axioms of ZFC. And we have the only non-logical symbol in ZFC theory is this symbol here, which represents the relation of inclusion, right? Any other symbol, any other concept is a concept that comes from logic. So you can see ZFC or set theory as an extension of logic, and we have a lemma, right, in ZFC that translates like pretty much like this. everything is a set. Everything math is a set. So you take, for instance, um, the natural numbers, right? The the natural numbers are built using just the empty sets. So in ZFC, the empty set is by definition equal to 0. And then we can use the axioms to build the number 1, that is the set with one element. Then we can use the 0 and the 1 to build the number 2, which will be this set right here. So in this go on, right? Um, So some people might get a little bit confused or annoyed by this construction, but the important fact is that this construction, using the axioms of ZFC, they give rise to mathematical objects who satisfy the piano axioms for natural numbers. And from that, from the natural numbers, we can build the integers. With the integers, we build the rationals and the reals and complex numbers, and basically every other thing that we deal with in mathematics. So that's why we say that ZFC or set theory is a foundation for mathematics. Right? So as I hope you might be wondering, is you might be wondering that what is about what is math, right? It's just about some mechanical rules, right, that a computer can follow. Well, kind of, but the essence of the nowadays construction of math is based on the axiomatic right? Axiomatic method. So I would like to remember everyone linear algebra, right? For me, it was quite a surprise when I found out that a vector did not necessarily need to be a vector, but right? We had this image, and when we first study properties of vectors, that a vector is something right in a Euclidean space, right, like an arrow and everything. But as we go deeper in linear algebra, we see that a vector is just something that satisfies the axioms for vector spaces. So a function can be a vector. And any other thing that satisfies the axioms for vector space is a vector. So that's how the axiomatic method works. And that's basically how math is done nowadays. So I hope I have given a nice introduction about logic and how it works. I'll come back to it later, but now let's go to Topos theory. So the question now is, what is a topos? Well, that is a very complicated question, because a topos can be a lot of things, and I like this analogy used by one of the authors that I'm using here. I'm going to talk about it in the bibliography, the references. That is a book that says Topos Theory, Sketches of an Elephant, because a topos can be seen as a lot of things, different things, a lot of different perspectives. So I'll try to give in a glimpse what three main features of a topos. They are very interesting, very and related to each other. So a topos can be seen as a generalized category of sets, as a generalized topological slash geometric space, or a generalized theory. So I'll begin by I'm using to introduce the concept of topos. I'm using a very nice paper written by Leinstein that is very good. So I'll talk about it later. So let's go a little bit faster because I'm getting out of time. So if you don't understand something, you can ask me. It doesn't matter. Let's take the definition. Elementary topos is a Cartesian enclosed category with finite limits and a subobject classifier. Here, that's nothing new. A topos is a category with some extra properties, which is it might be Cartesian enclosed, which means that it has power objects, right? And this relation is true, and a subobject classifier. A subobject classifier is a more is a new concept, at least it was for me. So basically, is an element of category which behaves like the set with two elements in the category of sets. And what is so important about the sets with two elements in the category of sets? It allows you to build subsets of any set, because subsets of any set in the category of sets corresponds to its characteristic function, which is the function CA, right? A subset of x here, subset A of x here, corresponds to a function CA, which assigns 0 to any element that belongs to A, and 1 that doesn't belong to A, and 1 if the element belongs to A. So a subobject classifier is kind of an object in a category that allows us to find um, objects that behaves like subsets. Example of topos, elementary topos. Set is the category of sets is the primordial topos. Given a small category A, the category of presships is a topos. The category of presships is just the category from functors from A opposite to set. Given a topological space, the category of sheaves on X is a topos. I will not go deep on what is a sheaf because it's not the main purpose of this talk, but I think it is good to talk about sheaves because many constructions in topos theory comes from constructions in topology, especially in constructions used in algebraic geometry when we are dealing with sheaves. So who doesn't he is not familiar with the concepts of sheaves, it doesn't matter. Um, so uh, how topos can be seen as a generalized category of sets. Let's look to the properties of sets. First, terminal object is a separator. That means that if f composed with x equals g composed with x for all x from 1 to x, big X in this case, then f equals g. Two, the terminal object is not isomorphic to the initial object. This makes sets a well-pointed category. Three, there is a set of natural numbers. I will not go in details, but uh, um, the existence of set of natural numbers is just can be proved if by the statement that there exist some objects that satisfy some axioms in terms of some diagrams, but at the end we just have some objects that satisfies the piano axioms. So we say they have natural numbers, a set of natural numbers, and epimorphisms split. Yeah, in extension, epimorphisms in set are surjections. In set theory, surjections split, right? And will be equivalent to the axiom of choice. So here we have some basic properties of set, the category of set, and Lovere. Lovere had the idea to use those properties above as axioms for set theory. In fact, um, if we use ZFC as foundation, we can prove that ZFC, the category formed by the ZFC theory, is in fact a topos that satisfies those four um, properties. So Lovere just said, what if we, instead of using ZFC as a foundation, why don't we use as a foundation for set theory those properties inside some category. So he gave the name to this other proposal, right, of foundation for set theory as elementary theory of the category of sets. And he proved, I don't remember if it was him or if it was somebody else, I think it was him. He proved that this formulation of set theory is almost equivalent to ZFC. In fact, ZFC is a little bit stronger than ETCS in the sense that um, everything that can be proved in ETCS can be proved in ZFC, but not the other way around. And we know exactly what portion of ZFC is equivalent to a TCS, and what we need to add to a TCS to get ZFC. So the important thing is that almost anything that can be proved in set theory can be translated to an arbitrary topos, not just a topos with the property of set. This, for those who studied monoidal categories and some more complicated structured categories, this is related. This property is relating to the possibility of talking about constructions we usually do in set theory. We can talk about than in any other topos, right? So this is related to the existence of, for instance, of monoidal categories, braided monoidal categories, and so on. And in fact, if we avoid the law of excluded middle and the axiom of choice in extension, in constructive set theory, almost anything that can be proved in the language of set theory can be translated to the internal language of that topos. For those who doesn't know what the law of excluded middle is the law who said that this proposition is true for any sentence in our language. It's true for any sentence. This is the law of the middle. and constructive mathematicians don't accept it. And this is related to computer-based proof systems. Uh, Fun fact, I think this is also very fun. In constructive, also called intuitionistic set theory, the axiom of choice implies the law of excluded middle. Right? This law that says that for any sentence, we have that sentence or its negation is true. So that gave motivation for us to think of topos as a generalized category of sets, right? Now let's talk about geometry. I will go even faster in this issue because we don't have a lot of time. So basically, if we have a well-behaved topological space, X, it can be housed, for instance, X can be recovered from the category of sheaves on X. Every sheaf is a topos. So topological space embeds into topos. The category of topological space is embedded into topos. That's why we can say that a topos is a generalized topological space. If we going to be more specifically, the functor assigned to any topological space its shape is full and faithful, right? And as I said before, many constructions used in Topos theory come from topology. So very brief, right? Because the relation between topos and geometry is, I will not go deep on that, but it is important to talk about it. So next, let's talk about morphisms between toposes. There are more than one morphisms between toposes. One of them is the logical morphisms, and the logical morphisms preserve everything that every structure in a topos. But we will use a different kind of morphism between topos that will translate some other characteristics, as we will see. So in this notion of morphisms is called geometric. A geometric morphism F between two tuples E and F consists of an adjunction, right? Like this, an adjunction. So we have a tuples E and a tuples F. We have a functor and a left adjunction to this functor, where the left adjunction also preserves finite limits. We say that this functor here with the upper star is the inverse image, and this functor here is the direct image. Just some terminology. We also say that a geometric morphism is an embedding if it is its direct image functor, this one, is full and faithful. In that case, we say that E is a subtopos of F. So a subtopos is just a full and faithful, let's say that, a full and faithful geometric morphism. Uh, this is interesting for those who have studied Grothendieck toposes, and I'm just introducing that because Grothendieck topos, to ask that for a Grothendieck to be a topos to be Grothendieck is a very mild condition, so a very strong condition. So basically, Grothendieck toposes has all the structure we need to work in many things. So as a definition, you can say that a topo is Grothendieck if it is equivalent to some subtopos of a presheaf topos. Well, I will end this talk by relating Topos theory and universal algebra. Right? That is, in fact, where lies most of the connection between Topos theory and categorical logic. And I'll begin with an example, right? The main example of algebraic theory, which is the theory of groups. We can say that the theory of groups is determined by um, an element, um, a unary function that is taking inverses, and a binary function, right? Which is multiplication. This is an operation symbol of arity zero, in other words, a constant. This is an operation symbol of arity 1. Here, arity of operation is just the number of variables, let's say like that, that goes that the symbol operates. And here we have an operation symbol of arity 2 plus some axioms. This is how we usually learn how the theory of groups works, right? And this was Lauver's idea, the same who developed the elementary theory of the category of sets, ATCS. So if we consider the category tau with finite limits and an internal group, in other words, a category tau with finite limits and an object X, a map from the terminal object X, selecting an object, right? An element of X, if we can talk about elements. A map, which we'll call the same as we called before, from X to X, and a map from the binary product of X to X, plus some axioms, this time represented in diagrams. Those axioms will turn X into something like a group, right, in the category tau. Um, if we take this category here, tau, built in that way, we can say that groups in set correspond bijectively to limit preserving functors from tau to set. So, more generally, given a finite product category E, internal groups in E are just limit preserving functors from tau to E. The main example, if I'm being too abstract with this, and if you're not familiar with the construction of internal groups in some category or internal monoids, basically what I'm saying is take this category and tau and give another category, for instance, the category of topological objects, top, right? If we functors, finite product, limit preserving functors from tau to top are bijectively correspond to topological groups, for instance, right? So we are internalizing the axioms of group into topological space, and more generally, in any other category. Tau is said to be the Lauver theory of groups. So we have another notion of theory arising here. And digression. What about logic? So here, I'll briefly try to say the difference between which is a very important difference in logic. That is the difference between, also in linguistics as well, but it is the difference between syntax and semantics. So far, when I presented the symbols, right? The symbols of logic and the rules of inference, we have been dealing with just the symbols itself without necessarily giving meaning to them. So that's it. That's the main difference between syntax and semantics. Syntax deals with symbols without being concerned with their meanings. So it's just about symbols, about the blah, 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 right? You do not need to give meaning to those symbols that I have presented to you. Syntax, when you are dealing with syntax, you just do the operations with them. By the other hand, semantics is exactly giving meaning to the symbols. So we state an axiom without being necessarily concerned with what the axioms, the symbols we use to build, to write the axioms. We usually are not at first concerned about their meanings. But when we are, we ask ourselves, what are the objects which satisfies the axioms? Um, the theory who is concerned with finding objects that satisfy some axioms is called model theory. So a model for axioms is just objects that satisfies the axioms. A model for the axioms of vector spaces are those objects which satisfy the axioms of vector spaces, and the same applies to set theory. The same applies to geometry. So a model to Euclidean geometry are just mathematical objects which satisfy the axioms of Euclidean geometry. So uh, that's the difference between syntax and semantics. And I'm saying this because this property here, when you say that finite limit preserving functors from tau to e are just internal groups, right? So they, in the language of logic, they those limit preserving functors, they give models to the theory of groups. And in classical logic, models of the theory of groups only existed in the category of sets. And in categorical logic, we can build models to the theory of groups in any topos, right? Or finite product category. And that's something that I should point. So I'm at the end. So let's say that every small category, in fact, every small category with finite limits gives rise to an algebraic theory. So we said that finite tau, the category tau with finite limits, and an object that behaves like this gives rise to the theory of groups. By the other hand, any category with finite limits will give rise to an algebraic theory. So we have a category for rings, for modules, for monoids, vector space, and so on. And the idea, right? We can generalize the idea and ask, if we give more structure to our categories, will we create more complex theories? The answer is yes. Um, the answer is, I'm going strictly to the answer, but it can be shown that every co-complete topos and every Grothendieck topos is co-complete. Uh, every co-complete topos corresponds to a theory. Those theories are called geometric theories. So, giving a geometric theory, models of that theory in another topos F correspond to geometric morphisms from E to F. E is called the classifying topos of the theory. So, given a geometric theory, it will have a classifying topos where models of that theory will correspond bijectively to geometric morphisms from the classifying topos to the topos where you want to find models of the theory. Particularly, every algebraic theory has its own classifying topos. And in topology, a point of a space X is just a map from one, the terminal topological space, to X. This map corresponds to a geometric morphism between the sheaves on one and the sheaves on X. But sheaves on one is isomorphic to set. So this gives us a definition. A point of a topos is a geometric morphism from set to A. I'm only saying that because in such perspective, the classifying topos of a geometric theory E can be regarded as its space of models, since a point of E is just a morphism, a geometric morphism from set to E. In extension, a model of that theory in the category of sets. And this is the last part where I will briefly try to say informally how I see homotopy type theory, although I haven't studied as deeply as I would like to, but here is how I see from the perspective of the foundation of mathematics. This is how I see homotopy type theory, right? Homotopy type theory is just a different foundation to mathematics. We will have different syntax, in other words, different symbols, different rules of symbol with those symbols, different possible constructions with those symbols, and a different semantical approach, which is quite deeply close to Topos theory, in fact, infinite Topos theory. But at the end, we change the syntax, we change the semantics, right? In other words, we change the symbols, we change the intended meaning of the theory, but as a result, we will have the same math, or almost the same math. Some things might change depending on how you build the theory. And of course, there is some other interesting things that I will not have time to go into. Just to end this talk, I might say that homotopy type theory is a different point of view from where we can sketch mathematical elephants, such as those used in differential geometry. And those are very complicated mathematical objects. And just by changing the point of view, changing the framework you're using, that's it. That language, the language of homotopy type theory, is kind of a change of framework to deal with some complicated objects, such as those that appear in differential geometry, in a synthetic way. What do I mean by synthetic? You don't need to go over all the troubles of set theory to build um, those objects. Those objects and their properties comes out of fabric with uh, built of fabric directly from the language of homotopy type theory. So uh, I think it is quite nice that it happens. And now I'm gonna say something very controversial. For me, it looks like that. We begin with classical logic and set theory, né? Our draft, our sketch of the mathematical objects. And then we try to use that to define what is category theory and toposes. And then we try to use that same language to define infinity categories and infinity toposes. But it is a very complicated uh, thing to define infinity categories and infinity toposes using the classical language of classical logic and the language of set theory. So homotopy type theory is kind of a framework who adapted or built to the necessity to talk about such complicated objects in an easier and um, less complicated, right, way. And I should remark that my point of view doesn't necessarily. I have all respect to the works of that those people who try to who did formalize what we understand by infinity categories and everything. But I think homotopy type theory is a good candidate into giving a treatment, formal treatment of those objects in an easier way, and um, I hope to talk more about it later. And that's it. The references I use are here. The book of Leinster, right? The article of Leinstein, an informal introduction to Topos Theory, the sketch of an elephant from Johnstone, theory, cites, and toposes from Caramello, and model homotopy type theory from Caulfield's. Those were the references. So I guess that's it. I hope everything went well because I didn't hear any complaints, any